In this video, we're going to look at the difference of squares in quadratic form. And if you recall, the difference of squares would be a squared minus b squared, and that can factor as quantity a plus b times quantity a minus b. And so if you look at an example, maybe we have something like this. Maybe we have, let's say we have 25 x squared minus, let's say 144 y squared. And so when we look at this, we look at a squared as 25 x squared. So then a would have to be, the square root of 25 would be 5, and the square root of x squared is x. So a is 5x. And b squared is 144 y squared. And so then b would have to be 12y. So then we have a squared minus b squared would factor as a, which is 5x, plus b, which is 12y, and then times that by quantity a, which is 5x, and then minus b, which is 12y. And so there would be the solution would be 5x plus 12y times 5x minus 12y. And so when we look at the difference of squares, right, this is a special form. And when we have special forms here, this type of special form has two terms. And these two terms are separated by a minus sign. And so now the question would be, are these two terms squares or not? Right, would be the question to ask yourself. And so when we look at a more generalized approach, we would have a more generalized setting we would have here. If I let, say, a take on the form u to some power n, then a squared would look at u to the n squared, and that can simplify as u to the power 2n. And if I look at b to be v to the m, then b squared would be v to the m squared, and that can simplify as v to the 2m. And so if you look at the difference of those two squares now, the quadratic form would look like this. We would have u to the 2n minus v to the 2m. And so that tells us that if we have two terms, and these two terms are separated by a minus sign, and the exponents are divisible by 2, then it's going to be the difference of squares. And we can apply the formula a plus b and a minus b to form that difference of squares of a squared minus b squared. And so if we think about an example here, let's look at an example like this. Maybe we have x to the 4 minus 16. And so now the question is, does this fit our special form? And is x to the 4 a perfect square? Well, the exponent 4 is divisible by 2, so yeah. And 16, the square root of 16 is 4. So we know that if I apply the formula a plus b and a minus b, then we would have x squared plus 4 for the first set of parentheses. And in the second set of parentheses would have x squared minus 4, which is okay, but we're not complete, right? Because there's nothing we can do the sum of squares, right? The sum of squares is prime in the real numbers, over the reals, over the integers. The sum of squares is prime. But the difference of squares we can factor further. And so that second factor, x squared minus 4, can factor more. And we can apply the special form again. So there's nothing we can do with the first set of parentheses, x squared plus 4. But the second set of parentheses, x squared minus 4, we can apply the difference of squares on. A squared minus b squared will always factor as a plus b times a minus b. And so we'll have x plus 2, the square root of 4 being 2. And the second set would be x minus 2. And now we're complete. Right? We've completely factored that expression, x squared, x to the 4 minus 16. All right, let's try another one. So maybe we have something like this. Maybe we have, let's say, x to the 8 minus 1. Well, 1 to any power is always 1. So 1 to the 8th power is going to be 1. So this is the difference of squares again. And we can apply a squared minus b squared as a plus b and a minus b. And so this time, the square root of x to the 8, 8 divided by 2 is 4. So we'd have x to the 4, and then plus 1, and x to the 4 minus 1 for the first step in factoring. And now we want to think about, can it factor more? Can it factor further? Well, x to the 4 plus 1 is a sum, and that stays, it's the prime. But x to the 4 minus 1 can factor further. It's the difference of squares. So it can factor more. And so we're going to factor another step. Well, there's nothing we can do with the sum of squares. So we have x to the 4 plus 1 in the set of parentheses. And now x to the 4 minus 1. Well, this time, x to the 4, the square root of x to the 4 is x squared. So we're going to have x squared plus, and the square root of 1 is 1. So x squared plus 1 in the first set of parentheses, and x squared minus 1 in the next. And so now this is another step, and we ask ourselves, can we do any more factoring? And again, the sum of squares. So again, this is the sum. This one is the sum, and that cannot factor further. It's prime. But this one is the difference. So we have x squared minus 1 can factor more. And so one more step in factoring. Well, we're going to carry that x to the 4 plus 1, that sum of squares, down. We're going to carry the x squared plus 1, the next sum of squares, down. But now that difference of squares of x squared minus 1 can factor as an x plus 1 and an x minus 1 in the set of parentheses. And so now this is complete. These factors are all prime factors. And so we've completely factored that expression, x to the 8 minus 1. Let's try another one. Let's say we have something like this. Maybe we have 16x to the 10 minus 25 x to the, let's say, 6. And so now let's think about this. Is that a special form? And so again, I see only two terms, and these two terms are separated by a minus sign. So I'm thinking, okay, sum of squares perhaps. And so now let's think about, are those the difference of squares? Well, 16 is a perfect square, so that checks out. What about x to the 10? Is x to the 10 a perfect square? Well, 10 is divisible by 2, so yeah, and 10 divided by 2 is 5. So x to the 5 quantity squared is going to make x to the 10. And so this piece here, the square root of 16x to the 10 is a 4x to the 5. And now what about the second term? 25x to the 6. Well, 25 is a perfect square, yeah. What about x to the 6? Is x to the 6 a perfect square? Well, 6 divided by 2 is 3. So x to the 6 is x cubed squared. So yes, it fits a form. And so in the first set of parentheses, we'll have 4x to the 5 plus a 5x cubed. And in the second set of parentheses, the difference, we'd have 4x to the 5 minus 5x cubed. And so now we think about, can we do any more factoring? Well, there's nothing to do with the sum piece. Now let's think about the difference piece. Can that factor further? And although 4 is a perfect square, x to the 5 is not a perfect square because 5 divided by 2 is not a whole number. And then we have the problem, additional problem 5, and 5 is not a perfect square, and neither is 3. So this would be complete here. We would stop at that point. Let's do one more. Let's think about having something like this. This is a little more complicated. Maybe you have something like parentheses, say 7x plus 3 squared minus parentheses 3x minus 5 squared, like that. And so one way of doing this problem would be to square it out, each term out, and then take the difference and see what happens, right? But we can look at this as being a quadratic form. If we let u equal 7x plus 3, then u squared is going to be 7x plus 3 quantity squared. And if we let v equal 3x minus 5, then v squared is quantity 3x minus 5 squared, like that. And so it fits our form. And so we'll have a plus b, and then a minus b, where this time a is 7x plus 3. So we have parentheses of 7x plus 3, and then plus b, which is the 3x minus 5, end parenthesis like that. There's our first set. And now the second set of parentheses would have parenthesis a, which is 7x plus 3, and then minus, and this time we have to be careful. When we minus more than one term, we want to make sure we indicate we're subtracting more than one term by putting a second set of parentheses in there. So minus a parenthesis, and the b term would be 3x minus 5. And so we're subtracting more than one term, we need to use the distribution property on that minus sign in the second set. And that we could do the same distribution property on the first set of parentheses, but when we distribute the plus sign, it's not going to change any signs. Right? We distribute a minus sign, it's going to change some signs around. And so here we would have in our first set of parentheses, now we're going to simplify. We have 7x plus 3 plus 5x, or 3x minus 5 would be 10x minus 2. There's our first set of parentheses. In the second set of parentheses, we have 7x plus 3. And then we distribute that minus sign. So we have minus 3x. And a minus times a minus is a plus 5. And so now we have 7x minus 3x gives us 4x. And 3 plus 5 gives us 8. And there would be the solution. It would be 10x minus 2 times parentheses 4x plus 8. And technically, we can do some more factoring. There's a greatest common factor of a 2 in the first set of parentheses, greatest common factor of a 4 in the second set of parentheses. And so if I take that 2 out, in the first set, we would have 5x minus 1. And taking that 4 out in the second set, we have x plus 2. And now we can rearrange. We can apply the associative property of multiplication and the commutative property of multiplication to allow us to rearrange things, right? And so we have 2 times 4 gives us 8. And then we have the 5x minus 1 times the x plus 2. And that would be the solution. So as long as our factors have a as long as our exponents are divisible by 2, we can apply the special form difference of squares, a plus b and a minus b. Okay, I hope this helps.